6.5, Fairness in Apportionment Methods. So we have some apportionment paradoxes. Citizens of Imaginaria will want the that would really expect from a fair apportionment. The house sizes increase, the state quota should all increase or remain the same, but never decrease. If one state's population is growing more rapidly than another state's population, the faster growing state should eat while the slower growing state gains. If there is a number of seats, adding a new state should not cause an existing state to gain seats while they lose them. However, apportionment methods are known to contradict these expectations. Before you decide on the right apportionment for imaginarians, or the apportionment paradigm, situation that occurs when an apportionment method produces results that seem to contradict reasonable expectation of fairness. There's a lot that the founders of Imaginaria can learn from U.S. history. The Constitution of the United States requires that the seats in the House of Representatives be apportioned according to the results of the census that occurs every decade, but the number of seats in the apportionment method is not stipulated. Over the years, several different apportionment methods and house sizes have been used and scrutinized for fairness. This scrutiny has led to the discovery of several of these apportionment paradoxes. The first one we look at is the Alabama paradox. At the time of the 1880 U.S. Census, the Hamilton method of apportionment had replaced the Jefferson method. The number of seats in the House of Representatives was not fixed. To achieve the fairest apportionment possible, the house sizes were chosen. The Census Bureau calculated the apportionment for house sizes between 275 and 350. There was a surprising result that became known as the Alabama paradox, which is said to occur when an increase in house size reduces the state's quota. Alabama would receive 8 seats with a house size of 299, but only 7 seats if the house size increased to 300. So, 19th recorded population at Colorado 9,700, and that of the U.S. as 76,212,168. Calculate the standard divisor and standard quota for the state of Colorado based on a house size of 356. So we would take the total population, 76,212,168 divided by 356, and we would get 214,079. And then to find the standard quota for Colorado, you take 539,700 divided by our 214,079 and get 2.5210. Now calculate the standard divisor and standard quota for the state of Colorado based on a house size of 357. So we take our entire country's population, 76,212,168 divided by 357, and that gives us standard divisor of 213,479. Taking our 539,700 population of Colorado divided by 213,479, we would get 2.5281. Did the standard quota increase or decrease when the house size increased? Well, it increased by a little bit from 2.5210 to 2.5281. Okay, consider the Hamilton method of apportionment. Explain how Colorado's final quota could be smaller with a larger standard quota. And we think that it must have been at the fractional part 0.5281 ranked lower amongst the fractional parts of the state's quotas. Then the fractional part of 0.5210 did. Or there were fewer remaining seats. So what we're saying here is when we did the calculation using this as a standard divisor, we either this 0.5281 was either lower than more states fractional parts than it was when we use this, or the increased divide or the decreased divisor gave a different state one more before Colorado, and thus there were less remaining seats, and we didn't get to Colorado at all. Suppose that the founders of Imaginaria decide to have a parliament that apportions seats to 4 political parties based on the portion of the vote each party has earned. Also suppose that party A has 56,700, B has 38,500, C has 4,200, and D has 600. We're going to use the Hamilton method to apportion 323 seats. So if we take and add this up, our standard divisor would end up being 309.5975, giving us 183.14101, 124.3550093, 13.56600, and 1.9380. So our lower quotas would be 183, 124, 13, and 1. And that totals to 321. So we have 2 more to assign. Highest decimal place, 0.938, 0.5660. So we'd have 14, 2, 124, 183. And that would give us a 323. So now let's look at 2. And we have A is 56,700. B is 38,500. C is 4,200. And D is 600. Our new standard divisor with the apportionment of 324 seats would be 308.642. Our new quotas would be 183.7079, 124.7399, 13.6079, and 1.9439. Lower quotas 183, 124, 13, and 1, which again gives us 321. Now we have to sign 3. So again, 0.94 is top, 2. Then we have 0.7399 here, 125. Then we have 0.7079, 184, and this would stay the same. And there we have it. Does this example demonstrate the Alabama paradox? If so, how? Let's see. Alabama paradox, which is said to occur when an increase in house size reduces a state's quota. So we increase the house size, what state's quota decreased? This one here. So yes. State C quota decreased from 14 to 13. The next paradox we talk about is the population paradox. It is important for the founders of Imaginary to keep in mind that the populations of the states change as time passes. Some populations grow and some shrink. Some population increase by a large amount while others increase by a small amount. These changes may necessitate a reapportionment of seats or the recalculation of state quotas due to a change in population. It would be reasonable for Imaginarians to expect that the state with a population that has grown more than others will gain a seat before the other states. Once again, this is not always the case. The Hamilton method of apportionment. The other states, or the population growth rate of a state, is the ratio of the change in the population to the original size of the population, often expressed as a percentage. This value is positive if the population is increasing and negative if the population is decreasing. Population paradox occurs when a state with an increasing population loses a seat while a state with a decreasing population either retains or gains seats. More generally, the population paradox occurs when a state with a higher population growth rate loses seats, while a state with lower population growth rate retains or gains seats. Notice that the population paradox definition has two parts. If either part applies, then the population paradox has occurred. First part of the definition only applies when one state has a decreasing population. The second part of the definition applies in all situations. Whether there is a state with decreasing population or not, it'll be easier to identify situations that involve a decreasing population. The other situations require the calculation of a growth rate. The reason that we don't have to calculate a growth rate when one state has decreasing population and the other has increasing population is that the increasing population has a positive growth rate, which is always greater than the negative growth rate. So note, the state must lose a seat in order for the population paradox to apply. It is not enough for a state with a lower growth rate to gain a seat, while a state with a higher growth rate retains the same number. So a state must lose a seat. Suppose that 18 respirators are to be apportioned to 3 hospitals based on their capacities. The respirators are allocated based on the Hamilton method in 2020, then reallocated based on new capacities in 2021. The results are shown in the table. How does this demonstrate the population paradox? So let's look. Okay, Hospital A has a growth rate of 2.53%. Hospital B has a growth rate of 7.76%. Hospital C has a growth rate of 2.67%. Okay, so looking at Hospital C, they had 16, now they have 15. They lost one even though they had a positive growth rate, while Hospital A went from 5 to 6. And while they had a positive growth rate, it was less than Hospital C. So essentially, Hospital C lost a respirator. Well, Hospital A gained one, even though A had a lower growth rate. Okay? So the growth rate of a population can be calculated by subtracting the previous population size from the current population size and then dividing the difference by the previous population size. Make sure to calculate the subtraction before the division. If you're entering the values in the calculator, it is helpful to put parentheses around the subtracted terms. So, the country of Ebonia has 3 states. Mudgeton, a population of 866,000. Walla Walla with a population of 626,000. And Dilbertia with a population of 256,000. There are 38 seats in the Congress of Ebonia. The apportionment of the seats is determined by Hamilton's method to be 19 for Mudgeton, 14 for Walla Walla, and 5 for Dilbertia. Census reveals that the population has grown, the seats must be reapportioned. If Mudston now has 921,000, Walla Walla now has 640,000 residents, and Delbertia now has 260 residents, how many seats will each state receive upon reapportionment? And how is this an example? So let's see. Doing our division, we get our standard divisor, going to be 47,921. Okay, when we started out, we had Mudston, Walla Walla, and Delbertia. And the original was 19, 14, and 5. Using our divisor, we get new of 19.2191. These are the quotas. 13.3553 and 5.4255. Lower quota, 19, 13, 5. 37, we have one more to assign, and it would go here, 6. So we have a situation where one lost and one gained. We need to calculate the growth rates. So our growth rate for Mudston is our new population of 921,000 minus our old population of 866,000. Then we're going to divide that by 866,000, and we get roughly 6.35%. Remember, when converting a decimal to a percentage, move the decimal place 2 places to the left. Next, we have Walla Walla, new population of 640,000 minus 626,000 divided by 626,000. And we have a growth rate of 2.23%. And lastly, we have Delbertia, new population of 260,000 minus our old population of 256,000 divided by 256,000 gives us a growth rate of 1.56%. Now note that Delbertia goes up with a growth rate of 1.56. Walla Walla goes down with a growth rate of 2.23, which is higher. So yes, this is an example of the population paradox, because Walla Walla loses while Delbertia gains with a lower growth rate. Next, we have what's called the new states paradox. As a founder of Imaginaria, you might also consider the possibility that Imaginaria could annex nearby lands and increase the number of states. This occurred several times in the United States, such as when Oklahoma became a state in 1907. House size was increased from 386 to 391 to accommodate Oklahoma's quota of 5 seats. When the seats were reapportioned using Hamilton's method, New York lost a seat to Maine despite the fact that their population had not changed. This is an example of the new state paradox, which occurs when the addition of a new state is accompanied by an increase in seats to maintain the standard ratio of population to seats, but one of the existing states loses a seat. The country of Narnia has grown from 2 states to 3. The House size of Congress has been increased by 5, and the seats have been reapportioned to accommodate the new state of Chippingford. The Constitution mandates the use of Hamilton's method of apportionment. Use this information in the following table to answer the question. So what is the original House size? Well, originally, in 39 plus 51, which is 90. What is the new House size? Well, we have 40 plus 50 plus 5, which is 95. How is this reapportionment an example of new state paradox? Well, let's see. Maruna gained a seat. While Beaver's Dam lost one, even though their populations did not change. The country of Neverland has 2 states, Neverwood with a population of 760,000 and Mermaid's Lagoon with a population of 943,000. The Constitution of Neverland requires that 84 congressional seats be apportioned by Hamilton's method. Neverwood has received 37 seats, while Mermaid's Lagoon has received 47. Recently, the island of Marooners Rock, with a population of 190,000, has joined the Union, becoming a state of Neverland. When Marooners Rock is included, 9 additional seats must be apportioned to maintain the same ratio of seats to citizens. Using Hamilton's method to reapportion the 93 seats to the 3 states, how is the resulting apportionment an example of the new states paradox? So it gives 38 seats to Neverland, 46 seats to Mermaid's Lagoon, and 9 seats to Marooners Rock. So, Neverland gained 1, and Marooners Rock lost 1, even though the population stayed the same. So that is why we are going here with this. When a new state is added, it is necessary to determine the amount that the House side must be increased to retain the original ratio of population to seats. In other words, to keep the original standard divisor. Calculate the new House size, divide the new population by the original standard divisor, and round to the nearest whole number. So our new house size equals the new population over the original standard divisor, rounded to the nearest whole number. New Mexico was admitted as the 47th state on January 6, 1912. Before New Mexico joined the Union, the U.S. population was approximately 76 million, and the House of Representatives had 391 seats. The new state had a population of approximately 300,000. Use this information to estimate the original standard divisor to the nearest hundred and the new population, the new house size, and the number of seats New Mexico should receive. Okay, so our new population is 76 million plus 300,000. I have one too many zeros here. Or 76,300,000. Now we had 76 million. We had 391 seats. So our standard divisor is approximately 194,400. So if I take our new population, divide it by the old standard divisor, which is the same, we want to keep the same, this rounds to 392. So one new seat. Mexico gets one seat, or New Mexico gets one seat. The ideal apportionment method would simultaneously satisfy the following four fairness criteria: the quota rule, avoid the Alabama paradox, avoid the population paradox, and avoid the new states paradox. We have seen that Hamilton method allows the Alabama paradox, the population paradox, and the new states paradox in some apportionment scenarios. So this example here, something's missing. Now we have seen in our examples that neither the population paradox nor the new states paradox occurred when using the Jefferson, Adams, and Webster methods. Turns out that all three of these divisor methods violate the quota rule. None of them ever causes the population paradox, new states paradox, or even the Alabama paradox. On the other hand, the Hamilton method satisfies the quota rule, but will cause the population paradox, the new states paradox, and the Alabama paradox in some scenarios. 1983, mathematician Mikhail Belinsky and Peyton Young proved that no method of apportionment can simultaneously satisfy all four fairness criteria. There are other apportionment methods that satisfy different subsets of these criteria. For example, the mathematicians Belinsky and Young, who proved the Belinsky-Young impossibility theorem, created a method that both satisfies the quota rule and is free of the Alabama paradox. However, no method may always follow the quota rule and simultaneously be free of population paradox. So, as you and your fellow founders of Imaginaria make the important decision about the right apportionment method for Imaginaria, do not look for a perfect apportionment method. Instead, look for an apportionment method that best meets the needs and concerns of Imaginarians. And that finishes this section.